Hi, I'm Norimasa Yoshida from NIhon University. This video shows the outline and demos of our paper entitled Visualization of Curvature Monotonicity Regions of 3D Bézier Curves in 2D and 3D. For details, refer to our paper linked in the description box. All the demos are captured in real time. In a 2D curve design tool, the shape of the curve entirely depends on how users place the control points. Even when using a CAD tool that visualizes the curvature cone, determining the placement of control points to ensure a monotonically varying curvature is not trivial. In our tool, proposed in 2024, the regions where the curvature varies monotonically are visualized in real time. By placing a control point within its corresponding region, users can easily generate curve segments with monotonically varying curvature. In this work, we extend this idea to 3D curves so that users can easily generate 3D curves with monotonically varying curvature. The blue region in the picture represents the curvature monotonicity region of control point P0 for a 2D cubic Bézier curve. If P0 lies within this region, the curvature of the curve varies monotonically. We briefly review the visualization method for the curvature monotonicity regions. The curvature monotonicity region is the area associated with a specific control point where d kappa over ds is either less than or equal to 0 or greater than or equal to 0. If we assume that the curve has no cusps and its curvature is non-zero, the denominator of d kappa ds is always positive. Therefore, we only need to check the numerator of d kappa over ds. The numerator of d kappa over ds can be expressed in Bernstein basis, as described in Saito's Computers and Graphics paper in 2023. In the visualization method, for a specific control point placed at each pixel in the window, we use a GPU to check whether lambda of t changes its sign by replacing the coordinates of the control point within the screen coordinates of the pixel. If it does not change sign, the curvature varies monotonically for the pixel. The blue region represents the curvature monotonicity region for P0. This is the region for P1. If P1 lies outside the region, the curvature does not vary monotonically. Similarly, this is the region for P2. And this is the region for P3. Through this visualization, users can know the region of a specific control point where the curvature varies monotonically. This slide shows our contributions. We propose a method for visualizing the curvature monotonicity regions of 3D Bézier curves, which was not previously explored. We present a 2D visualization method which displays the curvature monotonicity region on a constant depth plane for a control point of interest. It is fully interactive using a GPU for the demo cases. We present a method for directly visualize the curvature monotonicity region in 3D. Using a GPU, it is nearly interactive for 3D cubic Bézier curves. This is the curvature monotonicity region of P1. The viewpoint is rotated. The region is displayed at the intersection with a constant depth plane of P1. This is the region for P2. The viewpoint is rotated. If P2 is outside the region, like this, the curvature is not monotonically varying. And this is the region for P3. For curves with decreasing curvature, the region of P3 tends to be very large. This is the 2D curvature monotonicity region for P0. This is the 3D region, rotating the viewpoint. This is the 2D region again. You can observe that the 2D region is the cross-section of the 3D region. This is the 2D region for P1. This is the 3D region for P1. This is the 2D region for P2. This is the 3D region for P2. This is the 2D region for P3. This is the 3D region for P3. The visualization of the 3D region is limited by the specified bounding box. While we can increase the size of the bounding box, this also increases the computation time. A sufficient region is the area associated with a specific control point where Ci is either greater than or equal to 0 or less than or equal to 0. Ci is the coefficient of lambda of t, which is the numerator of d kappa over ds in the Bernstein basis. From the properties of the Bernstein polynomial, if Xi0, the first Xi, or Xnc, the last Xi, form the boundary of the sufficient region, it also forms the boundary of the curvature monotonicity region. This is the 2D curvature monotonicity region for P0. The white region is the 2D sufficient region for P0, rotating the viewpoint. The region is bounded by algebraic curves that are Xi0, Xi1, Xi2, Xi3, Xi4, Xi5, Xi6, and Xi7. This is the 3D sufficient region for P0. The region is bounded by algebraic surfaces that are Xi0, Xi1, Xi2, Xi3, Xi4, rotating the viewpoint, Xi5, Xi6, and Xi7. If the region is viewed from inside, dark coloring is used. Okay, this is the 2D sufficient region for P1. This is the 3D sufficient region for P1. This is the 2D sufficient region for P2. This is the 3D sufficient region for P2. This is the 2D sufficient region for P3. This is the 3D sufficient region for P3. Again, the visualization of the 3D sufficient region is restricted within the specified bounding box. The left figure shows an arrow proposed by Sugihara. Using our curve design tool, we designed the arrow so that the curvature of each segment varies monotonically. Due to an optical illusion, the arrow tends to appear right-forward facing. The right figure shows a rendered image of the arrow after it has been converted into a solid object. Thank you for watching.